Hello everyone, welcome back to Software Analysis and Design. Today we'll talk about the 4+1 views of software architecture, and then specifically about behavior modeling, about state charts, state diagrams. So first of all, let's check in. Where are you right now? Physically, where are you located as you're listening to this lecture? You at home in a comfy chair? Did you decide to take it out in the park, listening on your mobile phone, wherever that is? Just really notice your surroundings for a sec. And then, where are you in your mental body? Is it super busy and a lot of stuff going on? Or is it rather calm and chill today? And then, how do you feel? Where are you in your emotional body? Is there, I don't know, some frustration going on, oh yeah, it's another lecture to get done? Or is there some happiness and just some today's a good day? Just notice what it is. And then take a deep breath. And with the exhale, let it all slide away. It's not so important right now. We can just let it take a backseat for a little bit. Just be present with what's happening right now. Just feel your body. Just feel how the oxygen is going in and out as you breathe. Good. And then decide to be here now. Let's roll. So today we're going to look at the 4+1 view model of software architecture, and then also at the value of software architecture. So what is all of this for? And then we'll look at an example design case for a web shop. And then we'll look at behavior models, specifically the state diagrams, state machine charts, and then we'll do a little exercise at the end. To get started, let's meet Philip Kruchten. Philip Kruchten is a professor of software engineering at the University of British Columbia in Vancouver. And he has been in software architecture for a long time. He wrote this really famous paper that everybody cites about multiple views on a system. So you may remember from the first lecture that systems have multiple aspects. There are various ways of how we can show how the system is structured. So here in this little blueprint of a house, which you've seen before, there is a support structure model, and then there is an exterior covering model, and there's a plumbing plan, there are floor plans, and there's an electrical plan. All of those show different ways of how that system works. And then there's another set of models that shows how the system behaves. Like, in case door opens, what happens next? And a single language does not fit to capture all aspects of software systems. That's why we need different types of diagrams. So that's just as a little reminder. And now the 4+1 architectural blueprints was a IEEE software paper published in 1995. So it's been around for a while. It's been around for a quarter century. Yay, it's the anniversary of this paper. And the use of multiple views in software engineering allows to address separately the concerns of the various stakeholders of the architecture. So we have end users, we have developers, we have systems engineers, we have project managers, and so on and so forth. And they want to handle the functional and non-functional requirements separately, and then each of the 5 views is described along with a notion to capture it. The views are designed using an architecture-centered, scenario-driven, and iterative development process. So we're back to the loopy-loop models. And as we know, most real development models are loopy-loop in some way, because there will always be some kind of feedback loop that helps us improve in next iterations, whether those are agile sprints or whether those are longer iterations. And here on the right-hand side, you see that the 4 views. There's a logical view, a development view, a process view, and a physical view. And then you can describe and tie them all together by scenarios. The scenarios give you the examples for them. That's why it's 4+1 instead of 5, because it's kind of a special one. So the 4+1 view model says that software architecture deals with the design and implementation of the high-level structure of software. It's the result of assembling a certain number of architectural elements in some well-chosen forms to satisfy the major functionality and performance requirements of the system, as well as some other non-functional requirements such as reliability, scalability, portability, and availability. We will come back to those a few lectures down as well. And we can describe software architecture as a set of elements, forms, and then along with them the rationale and constraints that come along with software architecture. And such constraints could be for reliability, scalability, and so on. The elements can be our subsystems, and then the forms are like the different ways in which we need them. So here we have this 4+1 view representation. The logical view is the view of the system architect, and it shows the functionality, the decomposition of the system. The development view is more the view of the programmer, so it's the configuration management of the software. The process view is for the system architect, so we'll see the concurrency, the communication, and synchronization. And then the deployment view is about system engineering. It's the system topology, it's the delivery, installation, maintenance, performance, scalability, and throughput of the system. And in the middle, we see the use case view that is mainly for the end user. So these are the stakeholders that like to work with these different views. And there are different questions that come along with that. So the system architect wants to know, how is the system structured? And how does the system behave? And how does it perform? The programmers want to know, how can I build and configure it? And the system engineers need to know where to install and what hardware is used to do so. And the end user is mainly interested in what the system can do. So, for example, the structural view can be in class diagrams that have components, packages, and interfaces. We already did class diagrams. The development view has some versioning policies and file ownership, so that's more codey stuff. And then the deployment view has the physical model and mapping. So we have, for example, TCP/IP over Ethernet as a connector, and then the different components that get deployed for this model. And then in the behavior view, we can have message sequence charts. That's a difficult word. I'm going to stumble over that so many times. Message sequence charts and state machine diagrams, which we're going to talk about today, that will show us things like response time and frequencies. So in order to address these larger and challenging architectures that we come across in software as soon as we go beyond toy examples, the model has those 5 main views here in the original description of Philip Kruchten. The logical view is the object model of the design when an object-oriented design method is used. The process view captures the concurrency and synchronization aspect of the design. The physical view describes the mappings of the software onto the hardware and reflects its distributed aspect. And the development view describes the static organization of the software in its development environment. Finally, the description of an architecture, the decisions made, can be organized around these 4 views and then illustrated by a few selected use cases or scenarios, which then become the 5th view. Now, you may note that the description varies slightly in between the slides, and the reason why I'm using 2 sets of language to convey this meaning to you is sometimes one is easier and resonates a little more easily than the other one. But the sets of you who understand one over the other better are mixed. So therefore, I'm just giving you both. Here is the version that also includes the view on requirements, like which ones are more functional and which ones are more non-functional. And you see conceptual and physical are more for the logical and the implementation views are more for the functional requirements, and then the process and deployment views are more for the non-functional ones. And then on the left side, we see the more conceptual and logical ones, the structure view and the behavior view. And on the right-hand side, you see the physical or operational views, namely for implementation and for deployment. And the use case one just swims in the middle because it's kind of everything. You can get everything out of those. And we see that in that structural view, we have the perspective of analysts and designers, and this is done early at the requirements analysis. And the focus is on object-oriented decomposition, which is what you did last week. And then we have functionality as our main concern. So the artifacts here are class diagram, object diagram, and composite structure diagram. Then we get to the behavior view. So this is for system integrators, and it happens during the design stage. So it's process decomposition. We're concerned with the performance, scalability, and throughput of the system. Artifacts here are the ones that we're going into now. Sequence diagrams, communication diagrams, activity diagrams, state machine diagrams, interaction overview diagrams, and timing diagrams. And then we move into the more physical plane with the developer view for developers and project managers, also at the design stage. The focus is on subsystem decomposition, and the main concern is the software management. So here we use component diagrams and package diagrams to make software management easier. Last but not least, deployment view for system engineers at the design stage. So we want to map software to hardware. For that, we're concerned about the system topology, delivery, installation, and communication. And our artifacts are usually deployment diagrams and then network topologies. Network topologies are usually not expressed in UML. So with that, we get to the fifth one in the middle, the use case and scenario view. So here we have the end user perspective, and it's at the putting it all together stage. And the concerns are mainly understandability and usability. And the focus is on feature decomposition. The artifacts here are use case diagrams and user stories. Now, having those 4 views is a great start for getting your architecture out there. Another big thing that happens though, and this is also still work by Philipp Kruchten, is over time, we get into technical debt. Now, what is that? Technical debt is as you develop your system over time, you will notice that at some point, because of the evolution it goes through, you have less than ideal solutions for particular parts because you were fixing things over here and fixing things over there. And now both of those parts are fixed, but they are not super consistent or coherent anymore with the coding standard that was used down here. But that one down here, we don't have time to update right now because we need to deal with that new part over there. And so these things that creep in over time, they leave what we call technical debt. And some of that can be visible, like defects and low external quality, so the quality that the user can see. New features is also something that you can see, and additional functionality, but then technical debt is a lot of invisible stuff. So you'll find things like code smells. You'll find coding style violations. The code complexity increases. There's low internal quality. There's a documentation debt, which means it just didn't document everything. There's a test debt. You don't have test cases for everything. There might be a structural debt or an architectural debt that just says the architecture is not the best fit anymore for the current state of the system, for the evolution. And there could be a technological gap, which means, well, some of the technologies we use in the software system are just a bit old by now, not really up to standard anymore. So that is something that Philipp and colleagues treat in detail in the article Technical Debt from Metaphor to Theory and Practice, which is from 2012, so that's way more recent. And it kind of builds on the idea of what is the actual value of software architecture and how can we make sure to maintain that, as we know that over time technical debt is going to creep in. So with that, he has this other model that says missing value of software architecture. So the longer you work in software architecture, the more you may realize over time that managers don't like to invest a whole lot of time in redoing architecture or reevaluating architecture. And so the question is, What's the value of it in the first place? How can we argue for it? One of the most critical questions about software architecture is what is its actual value, and the difficulty in assigning an actual value and the effort spent working on it makes it much harder for software architects to convince those project managers or product owners to spend much effort on architecture-related activities, leading often rapidly to a large amount of technical debt. Technical debt is what I introduced you to on the slide before. And at any point in time, a software development team is faced with a choice. What do we focus on in the next release cycle or the next iteration or sprint? In the backlog of things not done yet, there are usually 4 kinds of elements, and those are the ones you see on the right. There are ones with positive value and with negative value, and there are ones that are visible and there are invisible ones. Negative and invisible, yep, bottom right, technical debt. Invisible but positive could be architectural or structural features. Visible and negative are defects, and visible and positive are new features and added functionality. And that is something that very often gets prioritized, especially from the client side, because they don't see that much of the other stuff. They want us to fix the defects and they want us to add the new features. They don't know about the invisible stuff so much, so that's where the software architects really got to step it up. So the visible value, green stuff. Most obvious items because the new features, services, functionalities, capabilities that should be added to the system. And sometimes also visible improvements in some of the quality attributes, like capacity, increase the response time, or improve the response time, make it shorter, and interoperability between systems. Then the red stuff is the software product is already released. It's likely to have some defects, hurting some customers directly or indirectly by giving negative press to you. Both of those visible ones have a cost to implement, and then some trade-off has already to be negotiated between parties here in terms of how much defect fixing relative to new features can we afford to do. And then it gets really tricky because then we get to the invisible stuff. So those are the yellow stuff: architectural elements, infrastructure, frameworks, deployment tools, etc. Known to the internal development team and architects, they often are deferred in favor of more green or red stuff. And their cost is often rather lumpy. They are hard to break down to small increments. And so while we do know that they add value in the long term by increasing future productivity and often key quality attributes, but that value is hard to define. And then finally, last but not least, the black stuff. Here are the elements that have a negative value and are invisible. Hardest of them all, big lumps of technical debt. They are the result of earlier architectural decisions that were wise and optimal at the time. So we're not saying, you were kind of lazy when you first did that thing. No, those were the best choices at the time. But with the current context, they're suboptimal and they can hurt the project in several ways, usually by reduced productivity or impact on the evolution of the system. The black stuff is known by the development team, but rarely expressed visibly at the level of key decision makers who decide the future release roadmap. Shortcuts or a mission to develop the yellow stuff increases the amount of black stuff, which then further prevents progress. So the yellow stuff people already don't like to deal with. It gets worse if you don't, because then you get more black stuff. And that's the short one of that. Now, where does it leave us? A compounding factor is that the various elements have many dependencies between them. So it actually gets even a little worse, especially dependencies of the green and the red stuff on the yellow or black stuff. Because that means if you try to take care of the visible stuff while ignoring the invisible, it gets worse. Time plays a crucial role as well. The value of delivering a new feature is immediate, and the value of developing a good architecture may be reaped only over a long period of time. Not so great in our instant gratification time. The key issue is then how much value is there in the yellow and black stuff, and what is really the value of software architecture. Some of the economic concepts, such as net present value combined with dependency analysis, should be able to reconcile that stuff, as in all four colors, so that we can make balanced choices. And there's a method called incremental funding method by Mark Den and Jane Cleland Wang that can be a step in that direction. I'm not going to dive into that one, but you see the reference at the bottom, and I certainly recommend to check out those articles. Most importantly, take away from this one is you have the 4 views for software architecture, 4 plus 1. And then you have these 4 types of things that you need to take care of for the value in software architecture and make sure that those get balanced over time. Good. So with that, we are in that interesting space between analysis and design right now in this course. So the analysis, just as a reminder, is for understanding and describing the domain. It describes the what, the main concepts and their relations. That's what we did in the class diagrams. And then design is for the synthesis of executable solutions. So it describes how a construction of a solution should work. And we get from analysis to design by first mapping out the problem space, the domain, with actors, actions, processes, responsibilities, and data. So we get to our use case diagrams, sequence and activity diagrams, which we're still going to visit, and then class diagrams. So elements of the analysis, what is it that is here that is in place? And then on the solution side, in the solution domain, we see the user interface design, we see the features, we see test cases, we see business processes and workflows, and then classes and their components, as well as their behavior and the data collections. Those are the elements of construction. So the thing is, you see a few things on the left and on the right, like the sequence and activity diagrams and the class diagrams, like both of them belong to the analysis as well as to the design part. And that's kind of the gnarly part to wrap your head around in this lecture. There is no clear line of when we step from one side to the other. It's a continuous process. So with the object-oriented paradigm, that one has been designed such that analysis and design models look alike. Like that is intentionally, not to confuse you. It's intention. And why? To keep consistency, to make modeling easier. So the classes that appear in a domain model can also appear in a design model. And they should, many of them, or most of them. And then there'll be more classes in the solution space, namely the classes that you weren't able to see before. So you see the component class diagram on the left, and then components, classes, and their behavior on the right. Now there are people who already put methods in a domain class model, and I'm okay with that. I've done that because there are processes and methods and tasks that we already know from the domain objects that will have to be carried out, replicated in the system. And so there is no harm in putting them in there early on. But essentially we'll move from what is there to how will it work. And that works via descriptive models to then prescriptive models. So at the beginning, we know, oh, we're going to need a sensor. And then the prescriptive model along with that says, well, we're going to need a class that can handle that input. So there needs to be a user interface design layer. Then there'll be a process, for example, ordering. So in the prescriptive model, then there will be a class that needs to handle that process, for example, in the business layer. And then in the data collection, that will be expanded to a data collection that is tables in a database. So that's all for the transition from what is there to how will it work. I just like this illustration. Just play with me, the wolf and the 3 little pigs. So what versus how? What? Think about the responsibility and the declarative parts, and the mechanisms are about the how. So the interface is about the what, and the implementation is about the how. Here's your implementation with the database in the cloud. Before, you had a sketch of the data that you need, and the how then tells us we're going to work with this in the cloud. On the right-hand side, the three little piglets and the wolf. What the piglets wanted to build a house. How are they going to do that? First, I think they started with the straw one that got blown over, and then the sticks got blown over, and then the stone, and he couldn't blow that over. I don't remember all of the story. I just couldn't resist putting the illustration in here. But you get the difference. What? Building houses. How? Sticks, stones, and straw. Good. After sticks and stones, let's check out a different example, a web shop. May hit a little closer to home for most of you. I know. So for that web shop, if we start with the use case overview diagram here, we see two actors. We see a customer and we see a shop owner. Customer can register, can log in, search, add item to cart, remove item from cart, and pay items in cart. The shop owner can log in, add item to catalog, remove item from catalog, be there for the payment of items, and then add to stock and package and ship. From there, we got to structure the functionality. So we got to define the subsystems of the functionality. The purpose of the system, so what's the decomposition into subsystems, and then providing support for those use cases. And we want to think in terms of responsibilities. For that, we can use component diagrams. We could also use class diagrams. There are different ways of how to do that. Class diagram, component diagram, I'm fine with either one. If we use class diagrams, that points toward object-oriented implementation. Component diagrams are being used for many ways of implementing things. So for the functional areas, version 0.1, we have identified as subsystems, so to speak, let's say our draft subsystems. There is a customer registration, there's a shop owner registration, there's a product catalog management, there's some stock control, and there's some payment. You might say, wait, why do I need two different types of registration? Can't they just all log in? Yeah, they can all log in. But the type of information that I have to hold for the customer is very different from the type of information I need to hold for the shop owner. They have in common that they both need a username, yes, and a password and that stuff, so they can have some user class that they can both inherit from, and it still makes sense to have both of those in separate functional areas. And then let's check the use cases against those functional areas. Let's see if we got covered. So customer registration, we got login and register, shop owner registration, login. Yeah, there wasn't really a register for the shop owner in the overview. Interesting. And then search can be carried out on the product catalog and on stock control. We can add items, we can remove items, we can add to stock, we can package and ship, pay items in cart. Now, what about add item to cart and remove item from cart? Where are we going to put those? Those will add another functional area, version 0.2 now, customer selection management. So we do need some kind of module that is going to support that or component. Now we are covered. And yeah, there were a couple more that we've excluded, like we are not doing the staff salary and all that kind of stuff. Now, the responsibilities of those different components are as follows: customer registration, entry, storage, and retrieval of customers, shop owner registration, entry, storage, and retrieval of shop staff, product catalog management, entry, storage, and retrieval of product data, customer selection management, register customer product selection. And the payment is responsible for handling the transaction between customer and shop. Stock control is responsible for registering available products in stock. And shop UI is to interact with the user. Now, let's quickly think back to Rebecca Wurzbrook. She was the one who told us how we're going to characterize classes. So let's quickly remind ourselves of those types. What classes are information holders, which ones are structurers, which one are service providers, which ones are controllers, which ones are coordinators, and which ones of those are interfacers. If you don't remember the definitions, hit pause for a second and read them through. She then also distributes these different types on a layered architecture. So this is one of our original slides. As you see the copyright at the bottom, there is a presentation layer, and then there's application, coordination, and control. There's business information and services, and then there is technical services. So the more complex our systems get, the more important it is that we introduce this kind of layered architecture to keep an overview and that it does not get too crowded in our individual diagrams. So here you see the elements that belong to the user interface, like all the windows, entry fields, push buttons, all that is a user interface type of class. And then the controllers and coordinators go into the application, coordination, and control. So login coordinator, registration coordinator, both of those. And then the information holders, service providers, and structurers, they go together in one layer, business and information services. And then last but not least, the external interfaces and the data interfacers go into the technical service layer. And then we have end-tier web applications. So here you again see the role. The interfacer is at the client layer, functionality is the user interface, and then techniques, for example, are HTML and JavaScript. So I know there are some new technologies out there that are not on this list yet. It's okay. The slide is from 2006, please forgive. But I thought she just did such a good job at illustrating this that I wanted to keep the original slide. In the presentation layer, the functionality is the page layout. Role is also an interfacer, and we can, for example, do that with Java server pages. Yes, I programmed those in 2006. I did. And for the control layer, there is the command over the software. So it's coordinator classes, and those can be done by servlets. Business logic can be for the business delegates. So we have the controller roles here, and that can be done in Java Beans. And then the data access for the domain model is done by information holders and structurers, also Java Beans, EJ Visa Enterprise Java Beans, for those of you who have never come across them. So just a type of Java Bean. And then resources are your databases and your enterprise services. So those are the service providers, and they can be done by an enterprise service bus or queues or a number of other ones. So with that, you have a pretty solid web layered architecture. And yes, replace this by newer technologies if you wish. All of that stuff is still out there and in use. And then we got to get to the identification of dependencies. So for the shop UI, we know that the customer registration, customer selection management, card data, and payment are definitely dependent on the UI, on the input from the UI. And then customer selection management and product catalog maintenance, they both are dependent on the product catalog. Customer registration is dependent on customer data. Stock control dependent on stock data, and shop staff registration is dependent on shop staff data. All right, so at the very bottom, you see that arrow says uses subsystem, uses depends on. And you can use the little package icons that are depicted here in green for organizing your class diagrams and your component diagrams, because each of those is going to have a bunch more classes. Remember, those are just your functional areas. So payment is going to need a lot of breakdown as well. All right, and then if we think a little further, we're going to realize, oh, we're also going to need a staff interface for this shop thing, because they see different views than what the user does. So we add those in. And then we can add the business logic layer and have a business process coordinator in there. And then we can again look at the typical roles across those different layers. So we start with the interfacers, move on to the coordinators, and then have a bunch of service providers. And at the bottom, we have the information holders. So that is the the detailed version of the web shop for the layers that you saw on Rebecca's slide. And then we got to think about the data domains. So for the customer registration, we're going to need their name and address and some kind of authentication. Shop staff, also name, and then authentication. Product catalog management needs some product IDs and prices along with it. Customer selection management needs a product ID and a quantity that they want to buy. Payment, that's a little volatile, that's still open. And then stock control, product ID and quantity. And now we can identify the support for the use cases at different layers in the architecture. So we go through our use cases again and check, are they actually supported on those different layers in the presentation layer, business logic, and data management layer. So that's where we walk through each of them and check whether we can actually make them happen. And then in the deployment diagram, you see that we have a backend system and an internet client, and both of them are connected via a local area network and then a gateway. And then maybe you have a firewall in the way, and on the back end, you have the other UI stuff, and then you have a database component that has the shop staff, stock, and customer database, as well as the product catalog. So that's what it looks like for your deployment. Now for the system dynamics, we're going to use sequence diagrams, which we'll get back to next week. But just to give you a very general idea, they describe the interaction in between components. So from the customer, we send a query to shop UI, then send a search to the product catalog, we get the matches back, then we can select items, and then we can update the selection, and then we can store the selection in the cart. So just tiny preview for you. And then we have to identify which ones are the active processes. So right now, the active components are the user interface parts, and then the passive components that only respond when called upon, those are pretty much all the others. With that, you had a thorough run through the web shop, all the architecture layers, all the way from the use cases to the different types of diagrams that we need. Minus which one? Yeah, minus the state chart. That was not in that web example, because the state chart is what we're going to do next after you take a brief break. So just hit the pause button right now, get up, stretch your legs. I'm gonna do the same. I'm gonna hit pause in my recording for a second and take a zip and shake everything out and get a few deep, deep breaths. Yo, you back? Good. Let's do this. So after a quick little break, let's jump into behavior models. And as you already know, we have those 4 views here, 5 views, and the zoom goes to the process view. And one of the ones that we see here is state machine diagrams. And those state machine diagrams express states of the system. Behavioral model in general depicts the states of the system and its classes and the impact of events on these states. So it indicates how software will respond to external events or stimuli. And to create the model, you should perform the following steps. First, you evaluate all use cases to fully understand the sequence of interaction within the system. So not just the use case overview diagram, but you actually have to go through the individual use cases. Then you identify events that drive the interaction sequence and understand how these events relate to specific objects. And then you create a sequence for each use case and build a state diagram for it. You review the behavioral model to then verify accuracy and consistency. So we're going to need both sequence diagrams and state diagrams. The reason why I'm flipping those two, we're going to do sequence diagrams next time, state diagrams today, because Most of them, for the systems that we tend to build, are a little simpler. Of course, there's always exceptions to the rules. So if you build embedded systems, they usually have a ton more states. If we look at systems that have a lot of interaction with the user, we often get away with less states. And today, we're going to get started with the states of a dog. So the dog may be sitting in the state sitting, then he sees squirrels, and then he starts barking. So then he's in a barking state. If he gets petted while he's barking, then he starts wagging his tail. And if he's wagging his tail and gets petted some more, then maybe sits back down. From wagging the tail, if he doesn't get petted anymore, it might take a while. He may wait to get pet a little more, or she, and then they might start barking again. From this very sophisticated entry-level state diagram, I'm going to take you through a couple more examples. So when we do a general order, then we're going to have our starting state on the left. An order gets created, and from there on, it can either get canceled or we can request a shipment. So same web shop. We're going to ship, and then it goes into a state of delivered, and then when the arrival gets confirmed, then we can close the case. So like most package services, when they drop something off, they'll scan the code, or they'll take a picture and see that it got delivered, or it got dropped off at the post office where you have to come pick it up, depending on which country you are in and how things are run there. And then you are in your final state, marked by the bubble around the black circle. A slightly different example for the bill of that one. Here we have a first idea of some of the elements. So we have an initial pseudo state, just means it's not a real state. We by default need something to start our diagram from, so we call that a pseudo state. And then there is transitions in between the states. And that transition is called invoice created here. And then we come to a state unpaid. So after the invoice is created, we are in the state unpaid, and then if the customer pays, then we move into the state paid. And if the invoice gets destroyed, then we're at the final state. I always say we are in the state paid. The system is in the state paid, obviously, not the system and I, or not you and I. The system is then in the state paid, or in the final state. So how are we going to do those? How are we going to identify the events with the use cases? An event is not the information that has been exchanged, but rather the fact that information has been exchanged. So a little example, the homeowner uses the keypad to key in a 4-digit password. We're back at like a security system for a house. The password is compared with the valid password stored in the system. If the password is incorrect, the control panel will beep once and reset itself for additional input. If the password is correct, the control panel awaits further action. So the underlying portions of that use case scenario indicate events that happen. Keypad, key in 4-digit password, password compared, control panel beeps. An actor should then be identified for each event. The information that is exchanged should be noted, and any conditions or constraints should be listed. Once all the events have been identified, they are allocated to the objects involved. So how are we going to represent those states? In the context of behavioral modeling, 2 different characterizations of states must be considered. First, the state of each class as the system performs its function. And second, the state of the system as observed from the outside as the system performs its function. So internal, external. The state of a class takes on both passive and active characteristics. And the passive state is simply the current status of all of an object's attributes. And an active state indicates that the current status of the object as it undergoes a continuing transformation or processing. So I can say my class customer has a state because I know what the name of the customer is, I know their ID, and I know their age and their address, or whatever I do know. Like that's a passive state. The bill being unpaid, that is an active state because it indicates that there is an continuing transformation or processing going on. The customer doesn't get processed. They might move to a different city at some point or a different country, but it's still a passive state of the customer because there is no ongoing transformation of the customer in that system. Elements that get transformed in the system, those have active states. And then there can be two different behavioral representations that can be discussed. So first, state diagram, that indicates how an individual class changes state based on external events. And then the sequence diagram, that will show the behavior of the software as a function over time. Today, the first one. So state machine diagrams. The objects have both behavior and state, or in other words, they do things and they know things. They do things, behavior, they know things, state. Some objects do and know more things, or at least more complicated things than other objects. And some objects are incredibly complicated, so complex that the developers can have difficulty understanding them. And to understand those complex classes better, particularly those that act in different manners depending on their state, we develop state machine diagrams. Which means if you have a lot of objects that have only passive states, this might not be worth it because they don't really matter. But if we have a little robot doing a bunch of things, that one has a ton of states, and that we definitely want to model. So UML state machine diagrams depict then the various states that an object may be in and the transitions in between those states. Well, what's again the other type of UML diagram that has states? Activity diagram. We'll get to that one too. So here's an example of a state diagram. And you see, this is the keypad example that we had the use case for. So after a key gets hit, we get into the reading state. Password gets entered, and then we get into the comparing state. And either password is incorrect and the number of tries is smaller than maximum tries, then we get another chance. Or if the password is correct, then we can select the next thing we want to do. Or if the password is incorrect and the number of tries is larger than maximum tries, then we get into a locked state. And apparently this timer can just, this lock state can just time out. So after that timer passes, we get another try or another 3, whatever the maximum tries is. So we see here that states are sets of observable circumstances that characterize the behavior of a system at a given time. Because you know where the system is at in the process according to the state. The state transitions are the movements from one state to another. Events are the occurrences that cause the system to exhibit some predictable form of behavior. Actions are what occurs as a consequence of making a transition. So if the password is correct, the next action is select. And the guards are Boolean conditions that must be satisfied in order for the transition to occur. All this example is taken out of Roger Pressman's book, Software Engineering: A Practitioner's Approach, McGraw-Hill edition 2014, if you want to look that up in more detail. Notation of this state diagram stuff. So on the left, you see a little ATM state machine. It can be idle. From the pseudo state, it goes to idle, and then it can either be active or it can be out of service with a few transitions in between. On the right-hand side, you see the notation elements. So for the simple state, we can just be waiting for the user input. And then there's a simple state with internal activities. So waiting for user input, and entry could have a welcome as a consequence, and an exit could have thanks as a consequence for those inputs. Composites with 2 substates. So for serving customer, we can break down into customer authentication and then the transaction part. And that same composite state is depicted at the bottom, but this time with hidden substates. Then you just see that little element of 2 further connected states. Then you know, oh, there's a whole nother diagram hidden behind that one. Further elements, the pseudostate for the beginning, and then there can also be a terminate pseudostate. So if there is no final state that gets reached by the click of a button or a user input and then the system doing something, then we can also terminate in a pseudo-state. There is an entry point to a pseudo-state, which is just general user entry, and then it goes to user input. And then same for an exit point of a pseudo-state, where the user exits. And then we have the choices. So two types. We have choices that can be based on conditions, and the conditions are here in the guards. So if balance is smaller than minimum, then we'll take that left arrow, and if balance is larger or equal to minimum, then we'll go to the right. And we also have choices based on guards with regard to the value that is in the diamond shape in the middle. So if TC, the value in the diamond, is equals T1, we go one route. If it is equal to or smaller than T2, we go another route. And if it's larger than T3, we go a third route. And then finally, we have some forks. Forks that split into transitions. So that means there's no guards. Both of those things happen. And then there's forks that join transitions. So when the parallel thing is done, we're coming back together. And then the transition to the final state on the right. Now, one more example. So you can look at those notation elements again and see how a couple of different things can be modeled. In this figure, we have a seminar class during registration. So we have the rounded rectangles that represent the states. You see the instances of seminar can be in a state of proposed, scheduled, open for enrollment, full, or close to enrollment, all of those. And then an object starts in an initial state, represented by the closed circle, and can end up in a final state, represented by the bordered circle. This is the very same notation as used by UML activity diagrams. Yes, we're going to reuse those elements. There is a lot of consistency across the UML. And then states are represented by the values of the attributes of an object. Yo, check. A seminar is in the open for enrollment state when it has been flagged as open and seats are available to be filled. And the transitions are then the results of the invocation of a method that causes an important change in state. That's quite a bit of info for this little seminar thing. However, the system is actually larger. So here's the complete life cycle of a seminar. There's the enrollment part with the proposed, scheduled, open for enrollment, full, and close to enrollment that we just saw on the previous page in more detail. But then there's also being taught after enrollment, and then final exams at the very end. And more details around that, with some guards, with some transitions. And because the life cycle of the seminar is so complex, figure 1 only depicts a part of it, only that enrollment part. Figure 2 has that entire life cycle, with figure 1 shown as a substate of the enrollment state. Now, if the system is larger, what if being taught also has a bunch of transitions? What if final exams also has a bunch of states and a bunch of transitions? Especially if you do online exams. I don't know, not especially if you do them. But you get the hint. Like both of those, being taught and final exams, also have a bunch more states. And for those more states, we're going to need separate diagrams again. So instead of doing this half thingy here, maybe it's better to just have one top level diagram like this diagram 3 here, where we have enrollment, being taught, and final exams. And then we're going to use more detailed diagrams for each of those states and model all the substates of it. Because that way you have this little very simple overview diagram, and then you have 3 more detailed diagrams that give you all the scoop that you need. So that's where you start thinking about how can you best break it down, like which abstraction level do you take in your diagram? And where do you do an overview diagram and then break it down into your detailed diagrams? A couple of additional references for the state diagrams. I've used the notation elements from umldiagrams.org, and there was another example walkthrough from Visual Paradigm, and then there's one from Spark Systems. I've used a little bit of their materials and they're all referenced on the individual slides. And here's just, ta-da, if you want to look at all of them, there you go. Now, your turn for this. For the amusement park entry system that we've been working with, the ticketing system, please develop a set of state diagram charts. Start with a top-level diagram and then choose to detail one or two of these states into composites with substates. See if you can make a use of all of the notation elements. I know that that sometimes feels a bit artificial, and there's always different options of modeling things, but the idea is to just practice using all those elements. So if you can really make use of all of them, try to find a way to design a fork and a join into those states if you can find an opportunity for it. Try and have a bunch of guards and model them in different ways, like model them with the attribute in a diamond shape and then one without an attribute in the diamond shape, just so you can learn a bit more about how mighty this notation can be. And honestly, if the amusement park entry system is too boring, go try it with a little robot. Let the robot do your favorite little thing, whether that is cooking a meal or whether that is go out play soccer or football, or whether that is doing acro yoga or balancing on a slack line. That'll be a hard one for a robot. You get where I'm going. Random shenanigans, like whatever you want your robot to do, see if you can break that down and think through in the steps of what states does that robot need to go through and what will be the next input. This is called computational thinking. Computational thinking is our pretty much strongest tool in software engineering. We need to complement that by systems thinking, which is also take a look at the whole. But right now, we're trying to decompose and understand how do we break this down into parts that we can conquer individually, and how do we express that in the states so that we can guide the system through the behavior that we want it to represent. There we go. Get on your exercise. Amusement park entry system, get me some state chart diagrams, and then go play with the robot. Figure out some state diagrams for a robot to let it do some simple things and see if you can make use of all the notation elements. Thanks so much. Let me know what you think. Leave your comments and feedback below. Make some requests for additional videos if that helps you. And I'll see you soon. Bye.